We'll take a few moments now to explore more about vertical and horizontal asymptotes. So an asymptote is a line that the graph of a function comes very close to but does not touch. There are three types of asymptotes: vertical asymptotes, horizontal asymptotes, and slant or oblique asymptotes. In this course, we're going to study only vertical and horizontal asymptotes, and I should make a disclaimer that a graph can actually cross the horizontal asymptote, but we will look at cases where that is not the case. So the line x equals h is called a vertical asymptote of the graph of y equals f of x if, as x goes to h from the left or right, y is approaching infinity or negative infinity. And these values, x equals h, come from the value where the denominator is equal to 0 for a rational function. So that is where a function is undefined. And that is, for us, where the denominator is equal to 0. So the function goes to positive infinity or negative infinity. That is, it's going to go either up or down as we approach this value of h from the left or right, as shown on this graph. So I have these two pieces, and to the right side of h, the graph is going up, but getting closer and closer to that line, so it's going up to infinity. And on the other side of h, the graph is going down to negative infinity. So it's approaching that line but never touching it. Very important to note that the graph of a rational function will never touch or cross a vertical asymptote. To find vertical asymptotes, if they exist, they are located at the values a rational function is undefined. So when we have r of x equals p of x divided by q of x, where p and q are polynomial functions with no common factor, and q of x is not equal to 0, then x equals h is the equation of a vertical asymptote of r if q of h is equal to 0. That's really just a fancy way of saying that the value of h is where the denominator is equal to 0. A rational function can have 0, 1, 2, or more vertical asymptotes because there could be many values that make the denominator equal to 0. Now there is a special case. If the polynomials p of x and q of x have common factors, then the rational function can have a hole at one of those zeros of q of x. So let's look at an example where we want to determine the vertical asymptote, if it exists, of each rational function, then state the function's behavior around the vertical asymptote. So if we have f of x equals 1 divided by x plus 2, this function is undefined when x plus 2 is equal to 0 or when x is equal to negative 2. So there is a vertical asymptote at negative 2. And we write the equation of the vertical asymptote as x equals negative 2. So what is a function's behavior around the vertical asymptote? Well, we could put in values as x goes to negative 2 from the right and as x goes to negative 2 from the left. We could also think about the transformation of 1 divided by x. We know that this graph is shifted left of 1 over x 2 units. But let's think about it. As x goes to negative 2 from the right and as x goes to negative 2 from the left, well, this graph looks like 1 over x, but it's just shifted left 2 units. So there's a vertical asymptote at x equals negative 2. And then there was a piece that was above the x-axis to the right of x equals negative 2. And there's a piece below the x-axis to the left of x equals negative 2. And so as x goes to negative 2 from the right, so from the right side, our graph is going up, which we say then that y is going to infinity. And as x goes to negative 2 from the left side, our graph is going down to negative infinity. Now I could graph this function on my calculator. When I press the y equals key, I have to type in 1 divided by, but then I need to put in parentheses the x plus 2 and close the parentheses, and then I can graph to see this resulting graph. And then f of x equals negative 4 divided by the expression x minus 3 squared plus 1. This is undefined when the denominator, x minus 3 squared, is equal to 0. And that's where x minus 3 is equal to 0, or x equals 3. So our vertical asymptote is the equation x equals 3. Now, to think about the function's behavior around this asymptote, let's think about what the transformation of the graph of 1 over x squared is. So remember that we are originally at these two pieces to the left and right of x equals 0 that both go up to infinity around 0. The denominator has an inside change, x minus 3, which means that's going to shift this graph right 3 units. And then this outer negative means that it's going to reflect across the x-axis. Now the 4 in the numerator means that it's going to have a vertical stretch by a factor of 4, and then it will shift it up 1. But so the impact of these transformations, think about this. So if I shift this graph right 3, or shift that vertical asymptote at x equals 0 will become x equals 3. And then the graph will reflect. So instead of the both pieces going up, now they're both going to be going down. They'll be stretched by a factor of 4, which means they're going to go down even quicker. And then it's going to shift up 1. So instead of that horizontal asymptote at y equals 0, it's going to be y equals 1. But the graph will go down to the left and to the right. And so as x goes to 3 from the right side, the y value will go to negative infinity since the graph is going down to the right side of 3. And as x goes to 3 from the left, y will also go down to negative infinity because it's going down on the left side of 3. Example C is f of x equals x minus 4, all divided by the expression x squared minus x minus 6. So to find the vertical asymptotes, we need to find where the denominator is equal to 0. That is where x squared minus x minus 6 is equal to 0. This is a quadratic equation we can solve by factoring. The factors of 6, whose difference is 1, would be 3 and 2. So we need the negative on the larger since the middle sign is negative, so x minus 3 times x plus 2 gives us that x minus 3 is equal to 0, or x plus 2 is equal to 0. So we have a vertical asymptote at x equals 3 and at x equals negative 2. And I've entered this on the calculator and actually copied the graph onto the slide. To enter this in the calculator, you have to put the numerator in parentheses, divided by, and then the denominator in parentheses, and then press graph. And you also want to do this graph in the Z decimal mode, which if you press zoom and 4, when you're in the Z decimal mode, you can see the graph a little bit better and how it behaves around the asymptotes. And so I have this graph, and notice that this graph is actually in 3 pieces. There is this imaginary vertical line through the vertical asymptote of x equals negative 2. And then there is also an imaginary line through this vertical asymptote of x equals 3. So the graphing calculator doesn't do a splendid job with graphing because it looks like the graphs actually stop, but it's just because it's so close to that vertical line that it can't distinguish it from that vertical line, which is the restriction. But if you're drawing this paper on paper pencil, you would need to understand that this graph extends downward to the right of x equals 3, and it also extends upward to the left of this line x equals 3. So we're graph in 3 pieces. Let me just describe them. So to the left of x equals -2, the graph is completely below the x-axis. As we go to -infinity, the graph is approaching this x-axis, or the line y equals 0. But as we're getting closer and closer to -2 from the left side, the graph goes down to -infinity. And then to the right side of x equals -2, as we get closer to -2 from the right, the graph is going up to infinity. And then it's going to cross at, it looks like 0, 2/3, and then it's going to stay above the x-axis, and then it's going to turn back up and go over to this line x equals 3, and it's going to go up to infinity as we get closer to that line from the left. And then on the other side of 3, as we get closer to 3 from the right side, the graph goes down to -infinity, but then it's going to come up and actually cross the horizontal asymptote of y equals 0, but then kind of go up and come back down to it. So eventually it's going to come back to this line y equals 0. And we're not really talking about horizontal asymptotes in this video right now. We just want to look at what are the vertical asymptotes and what is the behavior around those. And so we see that as x goes to -2 from the left, the graph is going down, so we say y goes to -infinity. As x approaches -2 from the right, y is going to +infinity since the graph goes up there. As x goes to 3 from the left, the graph goes up, so y goes to infinity. And then as x goes to 3 from the right side, the graph is going down, so we say y goes to -infinity. And then we have the function f of x equals the quantity x minus 5 divided by the expression x squared minus 25. Notice that when we rewrite this, that x squared minus 25 is actually x plus 5 times x minus 5. So this x minus 5 actually divides out as a common factor, and we get that this is 1 divided by x plus 5. So what that means is that because this x minus 5 divided out, the expression x minus 5 is equal to 0 at x equals 5. So we call this x equals 5 a removable discontinuity, which means there's not really a vertical asymptote there. There's actually a hole at this value of x equals 5. And that's because, again, it divided out. So the vertical asymptote actually comes where x plus 5 is equal to 0, which is at x equals -5. So x equals -5 is a vertical asymptote. But the function is still undefined at 5, but there's just a hole in the graph at x equals 5. So I've put this into the calculator, and you want to put the original function in the calculator, not the simplified version. In parentheses, x minus 5 divided by, in parentheses, x squared minus 25. And when we graph it, notice that we do get just these two pieces, it looks like anyway. And at x equals -5, there is an imaginary line. The graph does not cross. And so x equals -5 is our vertical asymptote confirmed by the graph. Notice that as x approaches -5 from the left, the graph is going down to -infinity. So we say y goes to -infinity. As x approaches -5 from the right, our graph is going up, so we say y goes to infinity. Now we won't have the arrow notation for the other restriction of x equals 5, but I do want to point out, I press trace on my calculator, and I input the value 5, and notice that y is equal to, there's nothing there. So that means it's undefined at that point. So at 1, 2, 3, 4, 5, you can't really see it. But the graph, if you were drawing this by hand, would actually have a hole there at 1/10 or 0.2. So there's a hole at 5.2, and then the graph would continue on. So the domain is still like -infinity to -5, union -5 to 5, union 5 to infinity. We still have to exclude that value of 5, but there's no vertical asymptote there. Now, horizontal asymptotes, we said that the line y equals k is a horizontal asymptote of the graph of y equals f of x if, as x goes to positive or negative infinity, y is approaching the value k. So that is at the far ends of our graph, what's the graph doing? If it's approaching a horizontal line, we say that y value is the horizontal asymptote. So horizontal asymptotes are asymptotic at the ends of the graph. That is the far right and far left. So again, that means they're getting closer and closer to this line. The function approaches k for very large or very small values of x. And as I stated earlier, a rational function can cross a horizontal asymptote. So to find horizontal asymptotes, it's actually based on the relationship between the degree of the polynomial functions and the numerator and denominator of a rational function. So if we have r of x as a rational function defined as r of x equals a sub m x to the m plus a sub m minus 1 x to the m minus 1 plus a sub 1x plus a sub 0, and that's all divided by b sub n x to the n plus b sub n minus 1 x to the n minus 1 plus all the way through b sub 1x plus b sub 0. Then we can say that as x goes to plus or minus infinity, r of x will behave as follows. So let me just make a statement here that the degree of our numerator is m and the degree of the denominator is n. And so we're looking at what happens as we go to plus or minus infinity. Well, if m is less than n, so that means that we have a smaller degree on the top divided by an expression with a larger degree, then the function has a horizontal asymptote at y equals 0. And that's because we're going to be dividing by a larger number. So as we divide something by a larger and larger number, the resulting value goes to 0. Think about it. If I have 1/2, 1/5, 1/10, 1/1000th, right? Those values, the denominator is getting larger, and so that means that my resulting fraction is actually approaching the value of 0. If the degrees are equal, so m and n are equal, then r of x has a horizontal asymptote at the quotient of the leading coefficients. So the quotient of those leading terms will be the horizontal asymptote. And then if m is greater than n, then r of x does not have a horizontal asymptote. So that is the numerator is now going to be growing quicker than the denominator, so there's not going to be a horizontal asymptote at that graph. There's not going to be a single number that the graph approaches. So a rational function will have at most one horizontal asymptote. So we will determine the horizontal asymptote of these rational functions just looking at their degrees. And I know I'm not really going into an in-depth explanation of this. There is an exercise in Top Hat that has you look at some functions and comparing what's happening as x gets really large so that you can see the resulting value. In this function, we have f of x equals 4x plus 3 divided by x minus 2. And so the key thing you're looking at is what's the degree of the numerator, what's the degree of the denominator, and how do they relate? So both the numerator and denominator have a degree of 1. So that means that the horizontal asymptote will be y equals the quotient of those coefficients, the leading coefficients. So that would be the quotient of 4 and 1. In other words, y equals 4 is the equation of the horizontal asymptote. F of x equals 4x squared plus 11x plus 6 divided by x plus 3. The numerator has a degree of 2. The denominator has a degree of 1. So since 2 is greater than 1, that means that there is not going to be a horizontal asymptote. And then finally, f of x equals x plus 1 divided by the expression x squared minus 4. The degree of the numerator is 1. The degree of the denominator is 2. So 1 is less than the 2. So that means that the horizontal asymptote will be y equals 0.